We are looking at a paper today titled Next Concept Prediction in Discrete Latent Space Leads to Stronger Language Models.
This is by Yuliang Liu, Zuhan Lin, and the team at LULMIA Lab, just published on February 10th, 2026.
And it introduces a new architecture called ConceptLM. So the core idea here is a shift away from, pure next token prediction, or NTP.
Right, it adds this higher level objective. They call it next concept prediction.
So instead of just guessing the very next word, it tries to predict a concept, a discrete unit that actually spans multiple tokens before it generates the text.
And it does this using vector quantization, creating this vocabulary of concepts in a latent space.
But the results are really the headline here.
Oh, absolutely. ConceptLM matches GPT-2 performance with 37% fewer parameters and 24% fewer training tokens.
It's essentially forcing the model to plan its semantic path before it ever commits to the words.
Efficiency, planning, and you can even retrofit existing models.
That's the 60-second summary. Now let's tear this thing apart.
Let's get into it.
Okay, so next concept prediction. We have been living in this world of next token prediction for, a decade now? It gave us GPT-3, GPT-4, Llama.
Everything, yeah.
So why are Liu and Lin trying to fix something that, arguably isn't broken?
Well, that's the big question, isn't it? Is it broken? I mean, if you look at someone like Jan LeCun, and the paper cites him a lot, his whole critique is that current LLMs are myopic. They're short-sighted.
Because they're just auto-regressive. They look at the context, calculate a probability, and pick the next syllable.
Precisely. It's like they're predicting the texture of the road 2 inches in front of the car, but they have no idea where they're going. They're not looking at the map.
And humans don't talk like that.
No. When you ask me a question, I don't mentally just guess the first sound of my answer. I form an abstract intent first. Like, okay, I need to explain the architecture, or I want to disagree with that point. That's the concept.
And then your brain decodes that concept into actual English words.
That's the whole hypothesis. Current models, they just skip that concept stage entirely. They go straight to the word stage and just rely on having trillions of parameters to kind of simulate reasoning.
But there's no explicit mechanism for planning.
None. And you see that fail in long context tasks, right? The model starts an essay strong, and then by paragraph 4, it's just lost the thread. It's hallucinating.
It forgot the destination.
Exactly. And people have tried to fix this. You see things like Megabyte or using diffusers for planning, but they usually just change the granularity, predicting bytes instead of tokens. ConceptLM is different. It's trying to build a real semantic vocabulary.
To find the actual, atomic units of thought.
That's the goal.
Okay, so let's talk about how it builds that vocabulary. The paper describes this 3-part structure, an encoder, a concept module, and a decoder. Walk us through that.
Yeah, think of it like a sandwich. At the bottom, you've got a standard token level encoder, takes raw text, turns it into continuous hidden states, just normal transformer stuff.
But instead of just sending those hidden states straight to a prediction head,
it sends them to the brain, the concept level module. This is where all the new stuff happens. It uses something called Vector Quantization, or VQ.
Okay, for the engineers listening who maybe haven't touched VQ since their signal processing class, give us a quick refresher.
Think of it like snapping to a grid. You have this continuous vector space, right? Infinite possibilities of floating point numbers.
Yeah.
VQ just forces those vectors to map to the nearest entry in a fixed predefined list, a code book.
So it's like taking a color wheel with millions of gradients and forcing every single pixel to be one of, say, 64 specific Crayola crayon colors.
That's a perfect analogy.
Yeah.
The model creates this code book, which is just a learnable matrix of vectors.
Yeah.
It takes the encoder's output, chops it into segments, and for each segment, it finds the closest Crayola color in that code book.
And this is the crucial part. It's not one-to-one with tokens.
No, absolutely not. That would defeat the whole purpose. They use a chunk size, which they call toll. In their main experiments, tolls is 4.
So one discrete concept from the codebook represents the semantic meaning of 4 tokens of text.
Exactly. It's a compression step. It might see the cat sat on and map that entire phrase to a single concept ID, maybe concept 42.
So the model now has 2 jobs running at the same time.
A dual loop. Job 1, predict the next concept. That's the high-level plan. And job 2, use that predicted concept to guide the generation of the next 4 tokens.
This all sounds great, but I remember reading the section on information leakage and thinking, okay, here's the headache.
Oh, it's a massive headache. It's the classic causality problem.
Right, because if you're compressing 4 tokens into one concept, you have to see all 4 tokens first to know what the concept is.
Exactly. Let's walk through it. You're at token 0. You want to generate tokens 1 through 4. To do that in this system, you first have to predict concept 1. But concept 1 is defined as the compressed version of the very tokens you haven't generated yet.
You can't compress something that doesn't exist.
Right. And if you try to do it during training, where you do have the future text, you're cheating. You're showing the model the answer key. The model learns nothing useful. It just learns to copy.
It becomes a self-fulfilling prophecy. I predict the next words will be, "the cat sat on," because I just peeked into the future and saw them.
Which is completely useless for actual generation. So to fix this, the authors did something clever. They implemented this hard causal shift. They basically shift the concept sequence forward by k$1 positions.
Okay, break that down for me. What does that mean in practice?
They pad the start of the sequence with empty zero vectors. This forces the model to predict the next concept based entirely on the completion of the previous chunk of text.
So when it's standing at the end of one sentence, it has to guess the concept for the start of the next one without any peeking.
Correct. It cleanly separates the planning from the execution. The concept module looks at all the history and says, okay, based on the vibe of the last paragraph, the next semantic block should probably be a counter-argument. It passes that intent vector to the decoder.
And then the decoder's job is much simpler. It just has to find the best words to express counter-argument.
Yeah, it's a much more constrained search space than just guessing the next word from scratch.
Yeah.
And this constraint is baked into the math.
Right, the loss function isn't just standard cross-entropy anymore.
No, it's a composite loss. It's $, it's literal dollar, LNTP plus LNCP plus LVQ. You've got the token loss, the concept prediction loss, and a quantization loss to keep the codebook from collapsing.
So it punishes the model if it gets the words right but for the wrong reason. If the plan was bad, but the generated words were just lucky, the gradient still penalizes the concept module.
And that creates this really strong evolutionary pressure on the encoder to learn high-level semantics. It can't just look at local syntax anymore. If it does, the concept module can't predict anything useful, and the loss just explodes.
Okay, let's move to the benchmarks. Because a cool architecture is only cool if it actually scales. They tested this against GPT-2 and Pythia.
They did. And the scaling laws, that's figure 1 in the paper, they look extremely promising. The big headline is parameter efficiency. ConceptLM gets the same perplexity as a standard GPT-2 model with 37% fewer parameters.
Wait, 37%? That's a significant number. We're not talking about a couple percentage points. That's over a third of the network just gone, with no loss in performance.
And it gets better. 24% fewer training tokens. If you're training a foundation model from scratch, your data is often the bottleneck. Needing a quarter less data to reach the same level of performance is a huge deal.
What about compute? The FLOPs?
19% fewer FLOPs. So it trains faster, it uses less memory, and it needs less data. It's a win-win-win.
Okay, but what about the zero-shot stuff? Sometimes these compressed models get really good at perplexity, but then they can't reason.
That's always the fear, isn't it? But no, on Lambda and the AI2 Reasoning Challenge ConceptLM actually outperformed the baselines.
ARC is tough. That's like grade school science questions that need actual world knowledge.
Yeah, and it really supports their hypothesis. It suggests the concept layer is genuinely doing some of the reasoning work. It's handling the logic in this abstract latent space and just leaving the token layer to handle the grammar.
This is all great for people training from scratch, but now for all the engineers listening who are, sitting on a pile of Llama checkpoints and thinking, I can't afford to retrain a model, segment 5 of the paper is for you.
Ah, yes, the continual pre-training experiments.
Yeah.
This was my favorite part of the paper, honestly. They took Llama 3.18b, a totally standard, off-the-shelf token prediction model, and they retrofitted it.
They performed brain surgery. They just inserted the concept module layers right into the pre-trained model.
And then, get this, they trained it for only 9.6 billion more tokens.
For an 8B model, that's nothing. That's like a warm-up lap, a fraction of what it took to train it initially.
It's tiny, a tiny amount of data.
Yeah.
But it worked. The model successfully adapted to this new concept mechanism. It actually started using those latent planning layers.
And the performance, it went up.
Yep. Across MMLU, ErrorCC, Squad, a whole bunch of them, they saw an average improvement of 0.4 points.
Now, 0.4 points.
Yeah.
That doesn't sound like a lot on its own.
It doesn't. But in the world of foundation models, trying to squeeze more performance out of a fully converged model like Llama 3 is incredibly hard. Usually when you mess with the architecture and fine-tune like that, you get catastrophic forgetting.
Yeah.
The model gets worse.
Right.
Here, they added complexity, they trained for just a few hours, and they got a measurably smarter model.
It almost implies that this concept planning ability is already dormant inside these big models.
That's the takeaway. The semantic information is there in the weights. They just lack the dedicated mechanism to use it explicitly.
It's the system 2 argument. The ability to plan is there. It's just buried. The concept module just gives the model a dedicated workspace to do that planning before it speaks.
Exactly.
Let's dig into the ablations, because I'm curious where they actually put this module. You can't just slap it on top, right?
No, and they found that the insert depth matters a lot. For their Pythia 160M model, the sweet spot was about 3/4 of the way through the network.
Why there? Why not at the beginning or the very end?
Well, think about what the early layers of a transformer are doing. They're processing syntax, morphology, just basic word associations. It's too noisy. There isn't really a concept yet. It's all just grammar.
So you have to wait until the model has actually synthesized the meaning.
Precisely. By layer 9 or 10 in that model, the hidden states represent much higher level semantic meaning. That's the perfect time to fork the process, quantize that meaning into a concept, and then use that to plan the next step.
And this whole structure also seems to help with longer context length.
Figure 4. This is the long-range modeling test. This was really cool. They pushed the sequence length from 512 up to 2048 tokens. And as the context got longer, the performance gap between ConceptLM and the baseline actually widened.
So ConceptLM got better relative to the baseline, the more text it had to read.
Yeah, because it's essentially reading a compressed version of reality. Remember, $24. For the planning module, a 2,000 token document is only a 500 concept document.
It's the difference between reading every single letter of a book versus just reading the paragraph summaries.
And since attention is quadratic, cutting the sequence length by a factor of 4 is a massive compute saving for that planning layer. It lets the model attend to concepts from way back at the start of the document without blowing up the memory.
One technical detail that surprised me was the codebook size. They said 1N, 6400.
Per segment, yeah.
Still, 64 just seems incredibly small for a vocabulary of all human thought.
It does, but you have to look at their segmented VQ strategy. They don't have just one codebook. They split the hidden state dimension into multiple heads, and each head gets to pick its own code from its own code block.
Oh, so it's combinatorial.
Right, so if you have, say, 32 segments, and each one picks one of 64 codes, the total number of unique combinations is 64 to the power of 32.
Which is a number larger than the atoms in the universe.
Okay. So the concept isn't one single value. It's a specific configuration of values across that whole vector.
It's a distributed representation that's elegant. It keeps the individual codebook small enough to train so every code gets used, but the total expressivity is basically infinite.
It really is.
So let's bring this all back to the big picture. We have a model that plans. It separates the what I want to say from the how I'm going to say it.
And it does it more efficiently.
Where does this go next? I mean, if you're a researcher at Lumae Lab right now, what's the next paper?
The obvious next step is just scaling it up. They showed it works as a retrofit on Llama 8B. What happens when you put this on a 400 billion parameter model? Does that concept layer become a true explicit reasoning engine?
Could you even see a world where the concept module is a totally different architecture? Like maybe a recurrent network or a diffusion model governs the concepts while a transformer just handles the token generation?
That's a fascinating thought. Since it's modular, you could just swap out the planner. You could even potentially have a human in the loop.
And that's where I wanted to end this. Interpretability.
Yes. This is the sleeper hit of this entire paper.
If these concepts are discrete, if code 42 reliably means introduce a counterargument, can we finally read the model's mind?
Theoretically, yes. Well, I mean, right now, to understand an LLM, we're looking at messy attention maps. But here, you have a clean stream of discrete IDs. We could, in theory, map these IDs to human understandable concepts.
You could build a dashboard where you see the plan evolving before the text even appears.
You could see the model is currently planning to validate user, then pivot to sales pitch, then close deal.
That completely changes the game for AI safety. You don't have to filter the final output. You can interdict the intent.
Right. If the concept stream signals deception or harmful instruction, you could just cut it off before a single harmful token is ever generated.
It's like a lie detector for the latent space.
It could be. Now, we still need to see if the codebook actually maps that cleanly to human concepts. Usually these things are messier than we hope, but the potential is absolutely there.
It really feels like we're inching closer to that system 2 reasoning everyone's been waiting for. Not by making the models bigger, but by making them more structured.
Structure is all you need.
Maybe. Or at least structure helps a lot.
Structure leads to stronger language models, just like the title says.
We'll leave it there. For anyone who wants to dive into the loss functions and the VQ gradients, the paper is Next Concept Prediction in Discrete Latent Space Leads to Stronger Language Models.
It's definitely worth a read if you're building or training these architectures.
Thanks for tuning in to this breakdown. We'll catch you on the next one.
See you then.